I'm Mark McHenry, and I work at Shared Spectrum Company. And we're a defense contractor. This is my first time coming to this meeting. But we got a project to figure out how to help DoD Systems share an electronic news gathering band. So the purpose of this is to kind of show you a little bit what we did in the project, and we're going to give an overview of the different types of sharing approaches, pros and cons. So that's what the talk is. So the next chart is an overview, the introduction. Am I supposed to flip, or? I wasn't trained before I came up here. So I'll give you a little bit about the background. You guys were kind of forced into the spectrum sharing thing. I'm sure it's annoying. There's not a great upside for you, but you were forced into it. I'll review a little bit of the background of the sharing that's going to happen. Then I'm going to show you the objectives of our project. I mean, the DoD, at least the guidance they gave us, was very favorable to you. And we'll go through all the things they tried to do to make it favorable for you guys. Then we'll kind of review some of the aspects of the ENG and DoD systems that is relevant to this sharing. This is actually a pretty complicated problem. There's a variety of ENG uses and a variety of DoD uses. So we came up with an approach which related to the DRL, the digital return link. There's actually some spectrum allocated on the side of the ENG band. We came up with a scheme to work on this, and then conclusion. Then I didn't put on the front, but Dennis Wallace he's back there. He helped us quite a bit on this. He actually educated us what are the characteristics of the ENG systems, and even more important, how are they really used? How many are operating at any one time in any one area? So the background is, it was this great, gigantic spectrum auction, AWS-3 auction, and I'm not sure exactly how it happened, but in the end, the outcome was DoD lost some spectrum in the auction, but they got the right to share the ENG band with you guys, the 2025 to 2110. And there's an FCC report and order or rules about how it's going to happen. And the good news for the electronic news gathering users, you have primary status. The DoD is supposedly come up with a sharing scheme that doesn't cause any interference or loss of service or even hassle. I mean, the idea of minimizing your hassle was in there. And the third bullet there talks about there's not really a deal been worked out, but it's going to be very simple. It's just a memo between the DoD and the broadcasters will set the deal. It doesn't have to go through public scrutiny or FCC process, and it can even be an evolving deal. So you have a lot of flexibility how you do the deal. So DoD got a lot of money out of the auction, and they're starting to modify their systems. Now, right now, there's not a lot of DoD systems that operate in this band, but in a year or two, there's going to be a lot of them. There's going to be aircraft, there's going to be ground systems, there's going to be a lot of systems. So even though they're slowly working to a resolution, the pressure on the DoD side to share is going to start really growing as they start getting these systems that are out there. And then I guess we got pictures. We'll talk about some of the DoD systems, but there's a range of platforms that are going to start using this band. So the objectives, this is the objectives of the project that we won from DoD, is to come up with a reliable, effective sharing scheme between ENG and DoD. And we actually focused on the hardest DoD problem, which is the airborne fast movers. They cover large areas and they come and go. But there's some easier DoD systems. We kind of just skipped those. Our project focused on the hard. And again, we assumed the ENG user was primary, and every meeting we have with the government, they would come to the 10th of a dB. Show me you don't impact the ENG, fractions of a dB in terms of their link range and the hassle. And one thing that I pushed was try to focus not just on the assignment process, but the enforcement. You can have a scheme that looks good on paper, but it's going to fail 10% of the time. And if the ENG answers to call up the general and say, you have to ground all airplanes and everything in the inventory in our band, that's not going to work. I believe the enforcement aspect, how do you recover from a mistake or narrow down what it is and how do you fix it? They're not going to fly the airplanes the next day to figure out what happened. So this whole enforcement issue has got to really be thought through from the very beginning and not as an afterthought. So there's a list there what our technical goals were. Again, we were very interested in the ENG receiver, not causing interference to the ENG receiver. And there was some words in there about Society of Broadcasting Engineer touch labor. They did not want to have the Society of Broadcasting Engineers constantly on the phone with DoD, either making assignments or resolving problems. The other thing is DoD wants to get some reasonable spectrum. You can invent sparing schemes that look good, but as soon as the airplane takes off, it's got to get out. You've really got to give some value to the DoD user. And that's a hard thing to do. A lot of schemes, they meet all the criteria except they fail to give much spectrum to the DoD user. And I know the ENG systems are evolving. We bought some of these OFDM systems and looked at them, but there's LTE and there's other uses. You'd hate to come up with an answer that didn't require any growth in the ENG side. And then the last one, you'd like to have zero costs. Now there's not going to be zero cost with any scheme. Any scheme has some costs, so we try to minimize that. So this is kind of preaching to the choir, but at least you'll know that we studied the ENG systems and tried to figure them out. I mean, there's a whole variety of users. And for us, the big issue is, are the antennas elevated or on the ground? Or do they have narrow beam antennas? And are they one way or not one way? So we went through all these, and it turns out the worst case to share with DoD is when you have a narrow pencil beam and you're not transmitting any signal. You get this hidden node problem. And it's very hard for DoD to know, are they in your receive beam or not. If you have omni to omni ENG systems, very easy sensing schemes will figure out, oh, there's an ENG close by. But you get these narrow 20 or 30 dBi gain antenna with no signal coming out of it. That is very hard to do spectrum sharing. And we know that the ENG users would like to have this pop-up capability, that in a moment's notice, they want to just turn the thing on and drive 100 miles, turn it on and get it to work. And that, again, is very challenging. DoD plans things days or weeks ahead of time, and once they kind of load the frequencies in their radios, for you to pop up and say, get off, it's not easy for them to do. They'd almost have to stop the mission and reprogram the frequencies. I mean, so to accommodate your pop-up requirement is very difficult. And the other requirement you have is, oh, we could be anywhere at any time, any place. Now, I think the reality is you're usually not any place. You're in urban, suburban areas. So we looked at that. And so the bottom thing there talks about the channelization. There's 7 channels in common use, and then on the sides there's these DRL bands. From what we understand, there was an ATSC standard to use DRL. This is data return link. If you put up a video system, you could send out a signal that tells you how strong the signal is. And it's not widely adopted, but if we put a beacon system on that, you'll see in a minute the beaconing approach. It really makes it easy for DoD to sense and avoid. Next chart shows the DoD systems. And of course, it's blank and there's no pictures, and I kind of apologize. DoD does not really want to share a lot of information with their systems, and you may have noticed that. And we work on these systems, and there's a lot of heavily classified systems. And some of these are frontline, right against it. So don't expect them to divulge a lot of information on some of their systems. Now, some of the systems are training or kind of behind the front lines, but once some of these systems are the frontline systems. So how does that impact this problem? And other than they won't tell you, which you don't really need to know, because you'll have contractors like us kind of bridge the gap. But some of these things are low power, some are high power, some are fast movers, some are omni. They have every system configuration you can imagine are represented, which makes it, again, challenging to find a sharing scheme that's economical for all of them. Now, we already talked about the concerns. They're also worried that if you came up with a system that would locate them, I don't know if you checked the 3.5 band. They put up these monitors on the coast, and the ships come by. They have to get out of the 3.5 band. There was a lot of resistance about, oh, someone will know where our ships are. Well, you have to really consider that as a requirement. You can't track them in training. Any scheme, they really want to be anonymous. When they fly, where they fly, and so forth. The good news is they don't always fly these systems every place. Most of these really high-value systems, they have very distinct training areas. Some of them, on the ocean coming in. So they don't need coverage everywhere. You could give them 90% of the value with very limited spatial access. Now, occasionally they fly over metropolitan areas, but most of their need is off in the middle of nowhere. So there does seem to be spectrum available, since you guys are not overlapping spatially. The other thing on the bottom here is they often are not connected to the internet. And I know there's a lot of interest in a database solution where you guys would load into the database, here where I am. Well, they're not connected to the database. It might take them a couple days, but to connect to the database, get your info, and put it in their plans and stuff. So it's just a fact. They're not always connected to the internet. So here's some numbers and engineering ease. Maybe it's not worth going through every line here, but what the purpose of this chart is we took how many dB away does the DoD system have to be from the ENG? That's really what it matters. If they're a 500 dB away, you can't cause any interference. If they're 50 dB away, you've got real problems. So the question is what is that separation required? So this table, I put a notional DoD system with 10 megahertz bandwidth, and I think it's 10 watts. Now, those aren't the real numbers. I put little, because I had to get through the DoD sensors, but I couldn't put real numbers. But it doesn't really matter. I mean, the answer is, if you sign up to cause really almost no impact, 0 dB INR, I don't know if there's a pointer here, you've got to be 159 dB away from the other guy's system. Again, it's that directional antenna from the ENG system staring at a 10 or 100 or whatever power the DOC system is. You have to be pretty far away. Now, if the ENG people would accept some interference, you might get 129 dB or some smaller number. So this is kind of the whole goal, is how do I know, how does a DoD system know he's within 159 dB of an antenna where he doesn't know where he's pointing, doesn't know the frequency, doesn't know anything? It's kind of a tough problem. So what this is, we're looking at kind of the worst case. Assume the DoD platform was airborne. And this is a propagation model. It's an ITU propagation model. And we look at the airplane at one altitude and another. One of these is a 1,000-kilometer DoD altitude against a 50-meter ENG receiver. And the right side is you have a 1,000-meter ENG system, which is on a mountaintop. It's not on a 1,000-meter tower, against a 1,000-meter ENG DoD height. And the dotted red lines are those two numbers in the previous chart. The question is, how far away does that airplane have to be? And there's two curves on those plots. There's a squiggly green, which is this ITU model. It goes up and down, up and down, up and down. And then there's a straight line. Where the line crosses the dotted line, if you read down, it says the distance. Of course, this is it's a log scale. But the answer is, you basically got to be at the horizon. If that airplane crosses the horizon, it's going to cause interference. These distances are pretty huge. So if you don't tell him the frequency, or if you're on, basically the DoD is going to get no use. He's got to know what frequency you're on and where that antenna is pointing. So the idea of just loading in a database some worst case assumptions is going to provide no value to DoD, and they're going to come back a year or two later and want to know, where are you pointing, are you on or not? So he's got to know this critical data. So okay, I've laid out a very tough problem, a lot of requirements. Is there any answer that makes sense for people? So I don't think there is one answer that's going to meet all these requirements. We're going to have several different approaches. They all have strengths and weaknesses. So I think they're going to end up building several systems, and they'll probably be unified together but running in parallel, and they'll have to be combined. So the first one is, let's just have a static exclusion zone. Let's do an equation and have a meeting, and you guys stay over, the DoD guys will stay over here on the other side of the hill. And that works for a few DoD systems. And I believe that was the initial negotiations between NAB and DoD, is that, well, let's just do the easy thing first. So that is a valid approach. It's the cheapest for everybody, and it's going to make a few of the DoD people happy, and you guys like it. So that one's going to happen. Maybe it's already. I keep looking at you. You know what's going on. This is happening.
Yep.
It has
13 sites.
13 sites. But the bad news is, it's really bad for DoD. They paid all the prices. I mean, it's only going to work for a few of their systems. The other approach that people are talking about is, let's have a database. So that means the broadcasters would get their smartphone out and say, I'm at this position, and they would type in a request, or possibly they turn the knob on their box, and they even have an azimuth indicator on their antenna, and that information goes into a database. And that database gets sucked in by DoD, and it gets pushed out to the platforms. And that's one of the biggest advantages of that is part of that presidential committee. When he read my pass things off, one of those things was called the PCAST study, the presidential study 3 or 4 years ago, when Google and Microsoft got in there and said, the database is the answer for all the spectrum sharing. And that was adopted in the 3.5 band. So the big advantage of this is there's momentum. This is a good way to go. And conceptually, it's simple. Everyone can nod their heads and say, I understand how it works. Let's do it, because it's easily understandable. But the disadvantage is it's a lot of trouble dealing with these databases. If your database isn't accurate, and the plane flies, you're going to be jammed. You can guarantee you're going to be jammed because they're flying enough that's going to cause problems. And it's also spectrally inefficient. If they don't know what frequency you're on, maybe you tell them I'm on, but you don't give them the frequency and pointing angle, they have to make a lot of worst case assumptions. Or if you tell them maybe where you're pointing but not the frequency, unless you give them total information on I'm on, where I'm pointing, when I'm frequency, it's very inefficient for DoD. And I think I put high operating costs. There's going to be a cost with this, X dollars per year, keeping it accurate and dealing with problems and stuff. And I guess if DoD would register the database and you would see them, it's probably going to be very one way. You're probably going to load what you want to do and never see what the DoD wants to do. So, but this will probably work. It's so appealing because they're doing it in the other band. This is probably going to happen. The trouble is it's still not spectrally efficient enough. You have to use, if there's ducting or any weird conditions, you're going to get interference. So they're going to start padding all these estimates. And it's going to almost lead to almost no spectrum for DoD, especially for these high-value platforms. These high-value platforms really want this spectrum. It's not like that they're just going to go away and give up. So this will probably roll out, but the other approach is sensing. And actually, everyone in this room has a dynamic spectrum access sensing device in your pocket. Because in the 5 gigahertz band, there's a thing called dynamic frequency selection. It's adopted all over the world. And because Google, Microsoft, bigwigs didn't like that in PCAST because it didn't favor their companies, it was put in a low list. But if you go to Cisco or any of the manufacturers, this is the approach that they like and want to do. And the advantage is, it doesn't have any assumptions. If I detect your signal coming up, then I know and I know your power, I know your prop loss, and I can figure out what to do. You don't need to do anything. It happens immediately. It's got every single advantage, except that now it's actually more expensive for DoD because they've got to modify their radios and put this sensing in there. So the advantage is it gives the absolute maximum spectrum efficiency. And I think it's got a lower operating cost. Once they paid, and they're putting this, that's our main line of business, is the dynamic spectrum access software for DoD radios. This project we have is very small for us. So, and then some of these big platforms, they're putting DSA on their systems right now for other reasons. So there's minimal cost, there's minimal administrative burden. Now the enforcement, I guess all of them have enforcement issues. So the disadvantage is it's cost them to put our software in. And the bad news also is if you maintain your OFDM waveforms, which are receive only, you have the hidden node problem. So the hidden node problem is just described here. So there's your antenna on top of a building or a mountain, and you have your beam pointing at your truck. Well, that DoD platform has no idea where your beam is pointing. He can detect your uplink, but that gives him very crude information on are you operating or not. So if you only sense on the uplink, you can show that it's a good spectrum sharing approach, but you're going to accept some interference. Some of the time, there's some geometries where that one fails. So if you really want to be protected 100%, you need to put a beacon on your OFDM systems. You need to transmit out, and the current DRL has a separate antenna which transmits omni. So what we did is you need to feed the DRL signal back to the antenna so it maps out your beam. So then the plane flies around, oh, there's the DRL signal. I must be in the beam. I need to get the heck out of that channel. So there's a trade here. Do you want to go retrofit? I don't know who pays for it. I know that's all you care about. But do we want to retrofit some of your old system? Now, if you went to LTE or some newer technology that has up and down link, you get the sensing for free. So it could be by the time you pay to put our we'd like to sell you the DRL thing, you're better off just getting the LTE. So that might be one approach, is you would convert to LTE, you would not have a hidden node problem, you make sensing work really well, and everyone gets the answer they want. But I think really for sensing to work well, you have to modify your operations. You cannot have the hidden node situation. So this is the box we built. And what this box is, it would go, you'd unplug your antenna cable to your antenna on your roof, you put our box on there. And what our box does is it injects out a DRL signal. And it's got all these filters and circulators so we don't jam you. So we spent about a year building a prototype box. It works. So we can send out a 1-watt beacon on either side of the DRL signal. And we also like to talk to your ENG receiver. if you change the frequency of your ENG receiver, we change the frequency of the DRL frequency. Right? The frequency of the DRL tells us what channel you're using. And we also hop to the other side of the band. If you go up to channel 1, we want to be on the high side DRL, so we don't end up jamming you. So we built these boxes. Okay, then the other thing you might want to consider, even if you don't want to use the DRL, just say you change the LTE, the other thing you might want to do is build spectrum monitoring in your ENG receiver. So I should back up. This one had a box called spectrum monitoring. I know what's going to happen is you're going to claim there's interference, and you're not going to have really reliable spectrum analyzer data. You're really not going to know why it worked, but you're going to swear it's DoD's problem. And we're going to get the finger pointing exercise. So on top of adding DRL, I think you should consider is requiring spectrum monitoring to be in there. And probably DoD would not want you to be monitoring them. You would allow them to put up a spectrum monitor, and this monitor is only looking for those 6 or 7 DoD signals and your signal. And if you would claim an interference report, you'd say, you'd write it down, I got interference. They would come back to these logs and try to figure out, well, really that was your buddy on the other's TV came up on your channel, or there's some other reason. And you would avoid arguments. And these spectrum monitors, you can buy them for a couple thousand. I mean, a spectrum monitor is not a high cost item. It'll cost more to negotiate with you and climb to your building than to buy that equipment. So even if you had an LTE system and didn't need the DRL, it could be what DoD says, well, if I look nationwide, there's 22 of your systems that really overlap the areas I want to fly. Let's instrument those so we have no more arguments when we start getting interference. So then DoD would connect to the internet. You'd provide internet access, and it would be really good if you would provide access to your ENG receiver and they could read off errors, read off frequencies. So you have electronic record. You know, what is the signal strength you were receiving? What bit error rate were you receiving? And even having, if I knew where your antenna was pointed, I put a compass on your receiver. The more you can automate, now maybe it's intrusive for them to collect. I don't know what you would lose though if they know where you're pointing and when you're turned on. Do you really care? I mean, they have spy satellites. If they really wanted to know, they would know anyway. But to avoid calling some general saying, your F-18s flew yesterday, I saw them and you can't fly anymore, and engaging the NAB to come untangle this mess, you can, by putting some technology in there, you can make nice interference reports, and these problems all go away. This is the wave of the future, this automatic spectrum management monitoring. So our company sells what's called DSA Software. And what this is, it's software that goes on the DoD radios that helps them avoid jamming, helps them, they can pool among themselves. And this is kind of a commercial. What DoD needs to do is, what our spectrum sharing software does is it takes the rules and limitations in the allocation table. It could be time of day, altitude, sensing base. We load those into the radio as an OWL file. And then the radio looks at the spectrum measurements and it looks at the GPS position and figures out, can I use the ENG channel or not? Can I use it or not? So right now there's several programs of record in the DoD getting ready to do this. So I think on your side, you might want them to do spectrum sensing because it gives you all these benefits. They're already doing it anyway for other reasons. So that's, I believe, the long-term answer. So this talks about the software. And it can change frequencies in seconds. It doesn't take very long for us to make a decision. We just finished a big demo in San Diego with 30 DoD radios, and all 30 radios as a network can move in a few seconds. And even if we would lose the argument on sensing, they're still putting it in the radios for the database. If you use a database approach and you give me some shape where I don't want you guys to fly because that's where my beam is pointing, they can load that shape into the DSA software and use a rule-based approach. So DoD is all set up to handle either sensing or database approach. So I think the answer is you're going to have to have a combination of these things. There's for the ground and low altitude DoD platforms, what you already have now, some analysis and a MOU where they operate is fine. For some of the low altitude DoD systems, the database will work, but these high altitude, fast moving DoD systems, I think you're going to want to use some type of sensing because they're going to be all over you. I mean, they're going to come up, fly over and around you, near you. You're going to constantly be overlapped, and they're not going to want to respond to a database. The database won't even work. They're flying. I mean, the mission's pre-planned. Unless you want to give up the pop-up use of the spectrum. But if you want to maintain that, probably want to go to something more sensing-like. So then someone's going to have to go through your whole inventory of ENG systems and figure out which ones need the beacon, because that's where they want to operate the high altitude platforms, which ones need the monitoring, and then come up with a design and a build a DoD. And I don't know who would do that. If you guys probably won't be proactive. It'll probably be on DoD to come to you with a proposal, but that's the next step in this, is to come up with this go through your inventory, figure out which ones need to be upgraded, which ones doesn't matter. And we've studied your systems. They're all over the place. They really are. And if they're all being used all the time, there's no spectrum available for any DoD use. So this temporal sharing is really critical to making this work. We believe they're only used a few hours a day. I mean, the usage is fairly low, but it's random and it's got a lot of bad characteristics because it's random and pops up. And, so here's kind of the uber figure how a system might work. So you have the ENG broadcaster up on the receiver, and he's installed either a DRL transmitter or at least a spectrum monitor. And all of a sudden he's got an interference report. An electronic message would be generated. It would pull off the channel you were using, the direction your antenna was pointing, the bit error rate, and would send that to DoD, this interference report. And it would go to a database, and then DoD would sign up that within X minutes or seconds they're going to fix it. So if they're hopefully they would go through this chain on the right. I don't know who would go to. It probably would go to DSA. I don't think you want to address every operational F-18 squadron. It would probably go to DSA. Where these would be aggregated. The report would immediately go down to the radio operator, and he'd have to have a policy preloaded to jump out of that channel. He'd have 20 or 30 policies. If this person complains, he's going to push the button and it's going to send it. If the platform is connected to the internet, it's going to get off. If it's not connected to the internet, then you're relying on sensing. Hopefully the sensing would work. But even if the sensing did fail, at least you would quickly fix the problem as soon as you got connected to the internet. So this has enforcement built in. It's connected to the operator. Right now, the DoD side doesn't have all these connections as well as your side. There's some building that has to go on both sides. So we built a box. The last part of this is to prove that our box wouldn't jam you. So this is this DRL box. There's a spectrum monitor built into it. We have a DRL transmitter, and right now it's just transmitting a CW, what's actually BPSK. We're not sending the DRL data back. And then there's 2 antenna connectors. Plus there's an Ethernet. The Ethernet is to pull the spectrum monitoring off. So what we did is we set up, and Dennis set this up, helped us set this up. We got a whole input to output. We have recordings of video signals. We send them to an ENG transmitter. We have a bunch of attenuators on the bench, and we send them all the way to a monitor. And we kind of did a baseline. This is the baseline configuration, which is the way you are now. So between your ENG transmitter and the receiver, there's just prop loss. For us, that's attenuators. And then we put our box in, and the question is, did our box diminish the prop loss? And there's 3 curves here. One is without our box, one with our box on there, and the third with our box turned on. And the axes are the total attenuation and the received power. We've done bit error tests, we've done TOV tests. So if you came to our lab, we could prove to you that we're not going to affect your operations. And there's charts here, signal quality and bit error rate. We've done so we have a box that won't impact your operations. And does the monitoring and the DRL thing. So in summary, you guys have been forced into the sharing approach. I'm sure you didn't sign up for it. You were forced. But however you got there, you're there. You have to come up with a way out of it. And then the problem is complicated because you have a variety of equipment types. They have a variety. There's all these different approaches. You should just accept. We're going to have a combination of these approaches to make it win-win for everybody. And we've got a prototype, and we're at the verge of ready to start doing testing. So I guess this is partly, I'll open myself up to questions.